thermal fluid engineering education.
Okay. Can you hear me? Can you hear me all right? Can you hear me?
Yes, we can hear you. Biswas?
Okay. All right. So I'll just get started here with a little bit of an overview of the presentation. So I will go over background and motivation for this work, and also describe some of the modeling objectives and how our experimental setup is put together, and what the kind of data that we collected for this. And then Dr. Biswas will follow with describing our modeling approach with the artificial neural network, the statistical model verification, and then the results we have been able to obtain so far, and conclusions. So the background here, essentially, why is it that we are trying to do this? So first of all, the question is, why do we want to make these biofuels, right? And so the idea is that we use lignocellulosic biomass, essentially the vegetables. And one of the reasons for this use is that biomass is renewable, right? So we can always grow additional biomass if we need to use it for fuels. Another reason is that it's carbon neutral, and the idea of carbon neutral is explained, is shown here in the right side of the slide. And when you have, let's say you have a tree, and somehow you get this tree to provide the fuel that powers your car, and your car is going to burn that fuel, generate carbon dioxide, which is released into the atmosphere. However, that same carbon dioxide can be reused by the new trees that grow, right? So we have the use of biomass actually promoting a cycle here, because the photosynthesis process capture carbon dioxide from the atmosphere, so that there is no net increase of carbon dioxide in the atmosphere if we use biofuels. That at least is the main concept behind that. And there is, of course, a large availability of biomass in most places in the world, and in many cases its use also helps to eliminate residues, right? And here we see some of the examples typical of biomass feedstocks that have been of interest: switchgrass, hybrid poplar, corn stover, DDGS. Now, what is the biofuel that we are trying to make? This here shows a table with a typical composition of aviation biofuel. So these are hydrocarbons, essentially, right? And the table here shows, and we also see illustrations here of some of the compounds that make up the composition of jet fuel. So we have paraffins and isoparaffins being a large component. Olefins, they are always there to some extent, but they are not really a desirable product. Aromatics and naphthenes are also a big part of jet fuel composition. So what we are aiming here, our target is to get an aviation fuel, or to get a fuel made up of hydrocarbons which contains paraffins, aromatics, and naphthenes. Now, there is a large variety of processes involving biomass that can actually produce hydrocarbons. And the one that we are going to be talking about today is called hydropyrolysis. Hydropyrolysis essentially, so pyrolysis here indicates thermal decomposition, so we require heat. So we are heating up the biomass. The hydro indicates the presence of hydrogen, molecular hydrogen. So we have biomass thermally decomposed in the presence of hydrogen. Typically, this process is carried out in the presence of some heterogeneous callus. So you gotta mix the solid biomass with the solid callus. And the products that are obtained usually fall within this range here. So we have BTX, so benzene, toluene, p-xylene as typical products. We also get some cyclohexane and alkanes, which, as you can see, are very close to the composition of jet fuel. So when we do this hydropyrolysis process, we do get the entire range of at least the types of molecules that we would expect in terms of jet fuels. Some additional advantages of hydropyrolysis: a large variety of molecular products produced. The liquid yields tend to be high. The you need pressurized hydrogen, but the pressures required are moderate. And the coking, the deactivation of the callus, takes place to little extent in this particular process. So there's lots of reasons why we want to use hydropyrolysis. Now, the specific motivation for this work, we want to be able to understand and to be able to predict how the hydropyrolysis products vary when we have different operation conditions for the reactor, different inputs. Okay, so for the model will be based on an artificial neural network, and this approach has the advantage or the ability to handle complex characteristics of input and output variables such as pressure and temperature. The idea is that we can converge to a solution quickly with a low error, and the ANN also has the ability to account for non-linear behavior. So Dr. Biswas will get into the details on how we assemble this model, how we put things together. But the overall goal here is to get some of the outputs, some of the conditions that we're putting at the inputs in this process, and to be able to tell, first of all, for those conditions, how much liquid product do we obtain? Not all of the biomass is going to become a liquid. How much of liquid we can produce, and also within the liquid, how much of that is a hydrocarbon? How much of that can actually be considered the typical model, the typical molecules for jet fuels? Okay, so summarizing here on this table, we have the inputs and the outputs that we studied and that we put in this model. Okay, so the hydrogen composition. So we need hydrogen. So the hydrogen atmosphere varying from 0 to 100%. Temperature in the range 350 to 550 degrees Celsius. Pressure 0.1 to 3.5 megapascal. And the nickel callus loading varying from 0 to 1.5 weight%. The outputs being, again here, the liquid content and the hydrocarbon content of the product. So we went ahead and collected this data. So these experiments were performed at the University of Washington. And here you see the experimental setup is a fairly complex experimental setup for hydropyrolysis. It's based on a fluidized bed reactor. So we have the callus and the biomass here. There is a screw feeder that feeds the biomass continuously into the system. Then there is an entire separation system that separates the char from the mainstream with a cyclone and then collects the products, basically using double pipe heat exchangers or condensers, and also glass beads. Now, once the product is collected, the high pressure gas is recycled back to the fluidized bed reactor with a gas booster. So here you see some pictures of this setup. So that this is how we collected the experiments for this work. Rafi, I need you to, you took control. I need you to move forward to the next slide, please. Dr. Biswas? Okay, so now we have just here a sample of the experiments, of the experimental data that we have collected. And what we show here is for a variety of catalysts, essentially the same conditions, how it is that the product's yields change. And we have on the top left here, charcoal, gas, liquids, and water as the main products. On the top right, we see the composition of the gases, and at the bottom, the composition of the liquid. So we analyze both the gas and the liquid, and we vary the nickel content all the way from no nickel to 1.5% nickel, with the support being a zeolite AgSM5. So the main result and the main conclusion of this set of experiments is that adding nickel as a metallic component to the support tends to drastically promote the methanation reactions that consume carbon monoxide and carbon dioxide and produce methane. Okay, so production of methane is essentially, so you get a lot of methane if you add a significant amount of nickel. At small nickel loadings, we do get more hydrocarbons in the liquid, especially more aromatics. Okay, so the small or no nickel loadings, we produce hydrocarbons in form of aromatics. As we increase this nickel loading, we produce methane. So this is just given here as an example for you to see one of the various sets of data that we used as we were building this model. So now I'm gonna let Dr. Biswas continue as he talks about the model that we employed.
All right, thank you. So with the data that was shown, we were able to go ahead and develop the empirical models using artificial neural network. And the layout of a neural network is basically includes an input layer, hidden layer, and an output layer, where basically you have the input that feeds into a weight, which is W, and sums with a bias B, and gives you a neuron with the activation function like a linear function. Now, and typically a hidden and output layers, they have more than one neuron. There's a set of neurons in there. So in that case, our weights, W's, are usually matrices, and our B's are typically vectors. And what happens is that the neuron from the hidden layer, they are fed into the output layer where you get the output neurons, and then you get the output results. Now, for us specifically, we actually utilized feed-forward neural network modeling for different hidden neurons using backpropagation algorithm. One of the most common algorithms used is Levenberg-Marquardt backpropagation algorithm, which adjusts the weights and biases to reduce the error. And this is the one that we use in our model. And we use a single hidden layer because it sufficiently predicts virtually any realizable function for our data set, and thus give us best fit to estimate the output based on the 4 inputs that we have. And again, for this, we use MATLAB for our model. And the way we verified our MATLAB model was by using statistical tools such as the mean squared error, MSE, and then the coefficient determination. And the way we determined the best fit was looking at the MSE, which was, we wanted to be as close to 0 as possible, and looking at the coefficient of determination, which we wanted to be as close to 1 as possible. Now here are our model results for liquid content, where we varied the number of hidden neurons. And based on that, we got our coefficient determination information and MSEs. And as you can see, most of our results for the most of the hidden neurons, we were able to get relatively close to 1 coefficient determination, typically about 0.85, 0.87 or so. However, our best result seems to be for 15 hidden neurons. And we can kind of see this closeness of fit of how well this model compared in this figure where we have the y-axis, which is our liquid content in percentage, and our x-axis, which is temperature in Kelvin. And the experimental data is shown as the blue circles. And here, as you can see, the results match relatively well with the our model results match relatively well with their experimental data, especially for higher number of neurons. And similarly, we can see a closeness of fit for this figure where we have y-axis is liquid content again, and our x-axis is actually pressure in pascals. And again, as you can see, for models with higher number of neurons, give much better they better matched with the experimental data. And then now here we have the results for hydrocarbon content, where again we vary the number of hidden neurons, and we got the results for the coefficient determination and MSE. And again, we can see that the results are actually pretty good. They're actually better than the liquid content model, where we actually get coefficient determination of 0.9 or higher. And our best model was actually for the 0.9 with 0.93 coefficient determination for 8 hidden neurons. And you can kind of see that in our figure. Again, our figure, we have x-axis is our y-axis is our hydrocarbon content in percentage. Our x-axis is our temperature in Kelvin. And again, you can see for the green diamonds are actually very closely matching with our experimental data in the blue circle. And then similarly, you can see that as well in this figure where again you have y-axis is the hydrocarbon content, and then our x-axis is pressure. Again, our models, especially for higher number of neurons, match pretty well with the experimental data. So in conclusion, most of our models show relatively good fit for the experimental data with the varying hidden neurons. The hydrocarbon content in liquid model happened to be much better compared to the liquid content model because it had relatively lower MSE or mean squared error and a coefficient of determination that was relatively high, typically about 0.9, 0.95, whereas the liquid content had not as low MSE and the coefficient determination was typically around 0.8, 0.85. And from here, we can actually select models that we could potentially use in the future to predict the production of liquid and hydrocarbon content from hydropyrolysis, and this could be used for design of experiment.
Okay, so just acknowledgements here, the student that actually did experimental work, Devin Chandler, a master's student that graduated the University of Washington, and the funding and support from TFAWS Biomass Solutions. Yeah, we TFAWS Biomass Solutions, warehouser in the University of Washington. So here just some of the references that we used. We want to thank you for the opportunity to do this presentation, and would like to well, open up for any questions that you may have.